All right, guys, so let's look at this in terms of a reaction. So it says the total amount of internal energy. Another way of looking at internal energy would be it would be the energy of a system. So remember, it's the energy of a system. Okay. In 1 mole of carbon and 1 mole of oxygen is greater than the internal energy at 1 mole of carbon dioxide. Okay, so in the reaction, carbon plus oxygen forms carbon dioxide. There will be a net release of energy into the surroundings. Okay, so here's an example of that. So the carbon and the oxygen are the reactants, and the carbon dioxide is the products. Well, if you remember, the change in energy equals the energy of the products minus the energy of the reactants. Okay, so that means that when you do the products here minus the reactants, your change in energy is going to be a negative, right? Because the product's internal energy is lower than the reactant's internal energy. Therefore, the energy of the reaction is going to have a negative charge. That's why that's negative. And it's going to be negative because what happened is the release of energy went released into the surroundings. So, a good way of saying this, a good way of explaining that would be like a bank account. Okay, when you are taking or releasing money from your bank account into the surroundings, say you're paying for food, then you're going to get that negative charge. You're taking money out of your savings account. You're releasing that money. Same thing, you're releasing the energy. Therefore, the energy of the reactant is going to be negative. In the reaction carbon dioxide yields carbon and oxygen, there will be an absorption of energy. Okay, so energy will be absorbed from the surroundings. So our products are carbon and oxygen, and has more energy than the reactants. And so in this case, you're going to do products minus reactants, and you're going to get a positive energy because the energy of the products is higher than the energy of the reactants. Therefore, what's happening is taking energy from its surroundings and it's adding it to the system. Therefore, its reaction is going to be positive. Just like when you are paid from your job, you're taking money from, say, your boss, and it's putting it into your checking account. Therefore, you're absorbing money or absorbing energy. Okay, so energy flow. When energy flows out of a system, it must all flow into the surroundings. When energy flows into a system, or out of a system, like we just said, when it flows out, the change in energy is negative. So again, when you buy something from your checking account, the change in energy is going to be negative. When energy flows into the surroundings, the energy of the surroundings is positive. Well, I mean, I'm subtracting from my system, but I'm adding to my surroundings. Therefore, the energy of the system is going to be negative, and the energy of the surrounding is going to be positive. So say you're taking money from your bank account and you're giving it to, say, Chick-fil-A. Okay. So you're taking money from your savings account, giving it to Chick-fil-A. Well, you get less money at the end and they get more money. Okay, so the surroundings is gaining energy, the system is losing energy. Therefore, the system, or the energy of the system, is negative. When energy flows into a system, it must all come from the surroundings. So the energy, you're taking energy from the surroundings and adding it to your system. And so that's like depositing money into your bank account. When you deposit money into your bank account, that's a positive thing. You're adding money. So when energy flows into a system, the energy of the system is positive. When energy flows out of the surroundings, the energy of the surrounding is negative. Okay, therefore the change in energy of the system equals negative change in energy of the surroundings. Okay, so energy diagrams are a graphical way of showing the direction of energy flow during a process. And so, therefore, if it's flowing opposite of the internal energy, it's going to have a negative total energy. If the reactants have a lower internal energy than the products, the change in energy will be positive. Okay, so if the reactants have a lower energy than the products, it will be positive. Well, in this case, the reactants have a higher energy than the products, therefore it's going to be negative. And again, here's another example. So if the reactants have a higher internal energy than the products, the change of energy will be negative. So it's just always good to remember that if you're going the same way as internal energy, therefore it's going to be positive. If you're going opposite ways, it's going to be negative. And that's the energy of the system, not the surroundings. The surroundings are opposite. So if the system is positive, then the surroundings are going to be negative. Okay? So energy is exchanged between the system and the surroundings through heat and work. Q equals the heat or thermal energy. W equals work energy. Q and W are not state functions. Their value depends on the process. So we follow the standard convention that change in energy with no subscript refers to the internal energy change of the system. So anytime you see this now, you're going to say that's internal energy, or the energy of the system. Okay, that's the energy of our reaction, not the surroundings. Energy entering the system through heat or work carries a positive sign. So energy that flows into the system is a positive sign. Remember, they're taking the energy from the surroundings. Work done on the system is going to be a positive sign. System gains thermal energy, that's going to be a positive sign. Now, if the system loses thermal energy or work is done by the system, so if the system has to do work, or energy flows out of the system, that's going to be a negative. That means that the energy, the internal energy, or the energy of the products is lower than the energy of the reactants. Okay? But here, the energy of the products is higher than the energy of the reactants. Yeah, okay. So think again, remember withdrawals are negative, deposits are positive. So when you're gaining thermal energy or work done on the system, energy flows into the system, that's going to be positive. System loses, work done by the system, or energy flows out, that's going to be a negative. Okay? So energy is exchanged between the system and the surroundings through either heat exchange or work being done. Okay, so we're going to use our example again of the billiard ball. We can define our system as the previously discussed billiard ball rolling across a pool table. The rolling ball has a certain initial amount of kinetic energy. When it reaches the other end of the table, the rolling ball collides head-on with the second ball. Assume that the first ball loses all of its kinetic energy, so it remains completely still. It has no kinetic energy at the point of collision. The total change in internal energy for the first ball is the difference between the initial kinetic energy and the final kinetic energy, which is 0. Okay? So the change in energy of the first ball is the difference between the initial kinetic energy minus the final kinetic energy. Okay? That's going to be 0, because remember, what goes in and must come out. The first billiard ball lost all of its energy. What happened to that energy? According to the first law, it must have been transferred to the surroundings. In fact, the energy lost by the system must exactly equal the amount of gain by the surroundings. The surroundings include both the pool table and the second ball. So the surroundings would be the second ball and the pool table. The pull table absorbs some of the ball's kinetic energy as the ball rolls down the table. Minute bumps on the table surface cause friction, which slows the ball down, converting the kinetic energy to heat. The second ball absorbs some of the ball's kinetic energy in form of work upon collision. So remember, this first ball is doing work to the second ball, but there's also heat loss by friction. Okay, so the white ball has an initial energy of 5 joules of kinetic energy. So its initial energy is 5 joules. 5 joules. The rest of the kinetic energy is transferred. As it rolls on the table, some of the energy is converted to heat by friction. So some of it's lost by friction, that 0.0 or 0.5 joules, and then the rest of the kinetic energy is transferred to the purple ball by collision. So the work, so change in energy. So remember, change in energy equals the change in energy equals the 5 joules minus the work, which is 4.5 joules, minus the sorry, that shouldn't be there. Negative 4.5 minus 0.5. So it's losing energy. Therefore, its change in energy is going to be negative 5.0. Okay, so it's a negative because what happened to the energy? The energy, all the energy from the kinetic ball went out to its surroundings, right? So that is why it's negative, because it went out in the surroundings. Say something was coming into the ball. Say if we were looking at the purple ball, well, the purple ball was absorbing energy. Energy was going into the system. Therefore, the purple ball's kinetic energy is positive. That's why it's positive. But here it's negative because it was actually doing work, and so it's going to be negative. It's losing energy. Okay? So, on a smooth table, most of the kinetic energy is transferred from the white ball to the purple ball with a small amount of lost in friction. So say we have a smooth table, really nice and smooth. A lot of the energy is still going to be done hitting to that ball. There's not a lot lost because of friction. Energy change for the white ball is as follows. So the change in energy is kinetic energy final minus the kinetic energy initial. Well, the final kinetic energy is 0. Okay? Because what happens is it loses all of its kinetic energy. The kinetic energy initial is the what we started off with. Okay, so we started off with 5 joules. That's what we started off with. We ended up with 0 because it completely stopped right here. Okay, and so that's going to be negative 5 joules. Kinetic energy is transferred to the purple ball is 4.5 joules. Okay, because what happened, this is the work done. It's the white ball is doing work to the purple ball. Okay, the white ball is doing work to the purple ball. That is the W. Well, what's the Q? The Q is the amount of heat lost through the friction. That's 0.5. Okay, so if I were asking about the kinetic energy transferred, you would just be talking about the work, not the heat. Kinetic energy lost as heat is negative 0.5. That's because Q plus W equals negative 0.5 plus negative 0.45. And so the total energy